So I want to continue the discussion of the Hecke operators, and we will define the associated recurrence. That, if you remember, there was this measure classification theorem that I'm not going to prove, and there were three assumptions in that theorem. If you have a measure on the unit tangent bundle of the modular surface that is invariant under the geodesic flow, we proved that. We proved that the microlocal lift is invariant under the geodesic flow and is recurrent under Hecke tree. We will have to discuss this, and satisfies positive entropy for all ergodic components. Then the measure is the uniform measure on the unit tangent bundle, and hence we've established arithmetic quantum unique ergodicity in the case. So today we will have to discuss the Hecke operators further. Yeah, this is what we want to do. And this was the first definition we gave. That's the classical definition. If you have just the modular surface, then this is a good definition of the Hecke operator acting on functions defined on the modular surface. But we want to be able to define the Hecke operator not just for functions on the modular surface, but also for functions on the unit tangent bundle of the modular surface. So that's why this definition is important. Yesterday we discussed that that's still the unit tangent bundle of the modular surface. We take a prime, and then we take a lattice, and we attach to this lattice all index P subgroups of the lattice. Then we take their homothetic equivalence classes and evaluate the function at those points. And we either average or use some other normalization, and we get a new function which is Tp of f evaluated at the original lattice. That's the definition of the Hecke operator. And maybe this is an important thing to point out. If you take C2 and P equals 2, how many index P lattices do you have, right? You could have the lattice generated by 2, 0 and 0, 1. You could have the lattice generated by 1, 0 and 0, 2. And you could have the lattice generated by 1, 1 and 2, 0. The order isn't so perfect, but you get 3 of them. And if you think about it a bit further, if you have this lattice, the subgroup of index 2 in C2, then you know that this lambda contains P times C2, right? Because it's index P. So this lambda mod P times C2 is a subgroup of C2 mod P C2, which is the affine two-dimensional plane over the field with 2 elements. And this subgroup here is a line in this two-dimensional plane. So you have as many index 2 subgroups as you have points in the projective line over the field with P elements, which is always P plus 1. So this is the right number if you want to have an averaging procedure. Okay, now this is pretty obvious. If you have this lattice, then you have these P plus 1 subgroups, and let me focus on this point here. If you replace your lattice lambda, if you replace your lattice C2 by C2 times G, right? If you replace your C2 and you have all the index T subgroups that we wrote down before. So there's lambda 1, lambda 2, lambda 3 in the case we discussed. And if you replace this picture by C2 multiplied by element G, then the index P subgroups of this guy will be the lambda 1 G, the lambda 2 G, and the lambda 3 G, obviously. And this helps you to prove that somehow you have a commutativity. If you take an element G in PGL2R, it acts on functions, right? By just composing the action of G with evaluation of the function. And you have this operator TP which acts on a function, so you can ask how the two behaved with respect to one another. And from this reasoning, you quickly deduce that the action of PGL2 and the operator TP commute with one another. You also need to check somehow that your TPF is really again a function on the homothetic classes, so that it's again a function on the unitangent bundle of the modular surface, but it's again related to this reasoning, and I want to leave it at that. Yes? Yes. Yes. Thank you. We just had 5 minutes in the end, but it's okay. So there's a corollary to this. If the SL2 action, capital SL2R action, commutes with the operator TP, then so does the Lie algebra. The Lie algebra is just sort of the derived element, the derived action. So, and there is a corollary to this statement, because we built our microlocal lift by defining this function phi twiggle out of a function phi on the modular surface. Phi was on the modular surface, then we worked hard and we got the phi twiggle. But this phi twiggle we produced by taking derivatives of phi and taking sums and stuff. So if your original phi is an eigenfunction for the Hecke operator, and you do all of this stuff, then the phi twiggle is an eigenfunction for the Hecke operator with the same eigenvalue. You haven't changed that property because of the commutativity that I just pointed out. Okay, now there's another story, another twist to the discussion of the Hecke operators. We can extend the space. We already did this once, right? We had the modular surface, we extended it to the unitangent bundle. But now I want to do this once more and bring in the p-helix. So here's the statement. If you take the product of PGL2R with PGL2QP, there's a lattice in that group, which is just PGL2C bracket 1 over P. So C bracket 1 over P, that's a ring of rational numbers, that's easy. And then you can take PGL2 of that. Again, what is that? You take GL2 of that, you know what that is, and then you identify two matrices if they differ by something, some constant multiple of that entity. So this is PGL2R, and we can embed this into the direct product of PGL2R and PGL2QP by sending element here diagonally to the element gamma gamma. And then you get the lattice in the product. And there's another claim, namely that when you look at the double quotient, you take this group and you quotient by the lattice on the left. And then you quotient by PGL2CP, which is a subgroup of PGL2QP and hence acts on this space. You quotient by this compact subgroup on the right. You get this double coset space, and that's nothing but PGL2R mod PGL2C, which is the unitangent bundle of the modular surface. So we just wrote things that look more and more complicated, but then in the end, when we really write down this, we have still the same space. This may be something to swallow, but yeah, it's an important step for what we will do, because it brings in another group action. It brings another group, right? Suddenly, if I don't quotient by the PGL2CP, then the PGL2QP acts on that space. And PGL2QP is a big group, so maybe I can use that. So a dynamicist always wants a non-compact group acting, because if there is a compact group acting, it's too easy and it's not useful somehow. So here one has hopes that maybe an arithmetic quantum limit has properties with respect to this p-adic group, which is a big group acting on, well, not quite on the unitension bundle of the model surface, but it acts on a slight extension of that space where you don't quotient out by PGL2CP. The proof of this is sort of a formal game, I would say. You just write down the abstract algebra and then you believe it. What do I want to say? If you have an element G in PGL2R, then obviously you can look at G times the identity and quotient out PGL2C 1 over P, right? You can consider to an element G in PGL2R this element, which maybe you can also quotient on the right by PGL2CP. So you have a map from PGL2R to this double coset space. And now you would like to know whether this map is injective. And of course the claim is no, it's not injective. Precisely because if you modify your G on the left by some element gamma in PGL2C, then you will get the same element. Maybe let's practice how this works. You take what you get from this. When you take this, you get this, right? When you take this, you get gamma G identity, and then this PGL2C 1 over P, PGL2CP. But yeah, we know of course that PGL2C is also an element in PGL2C 1 over P. So this gamma is in here, and you would say, so of course we can just kill this gamma because it's already here anyway. But that's not quite true, because when the definition of my PGL2C 1 over P considered as a subgroup of PGL2R cross PGL2QP is the diagonal thing. So when you want to get rid of this using this element, you get PGL2C 1 over P G gamma inverse. So this gamma sort of moves over to here. But now we are happy because this element is not only in PGL2C 1 over P, it's also an element in PGL2CP. So now we can get rid of this and replace it by the identity because it's in here. So we have to use both sides to make this work out. And then you can argue that this is really reversible, that it's an isomorphism. Yeah, it's an easy calculation. It's in the notes. Okay, now what is Kp? Kp is the CP. That's a new notation. You could say GP is the PGL2 QP. I just want to introduce the notation so that I can consider this quotient GP mod KP. We will consider that quotient, and we need to understand it later well what that quotient is. So here I do some slightly awkward looking calculation. KP is a compact open subgroup of the periodic group GP. So it's compact because CP is compact, and it's open because CP is open in QP. The element P1 is not an element in PGL2 CP. It looks like it is, but it's not, because the determinant of it is P, which isn't a unit in CP. So this is outside of KP, but you can look at this double product thing. And this is some compact open set in GP. So it can be written as a finite union of these cosets of one-sided coset spaces. And here's a concrete way of writing this. So it's KP times the original element, disjoint union of KP times these other elements. And had you not looked at P1, but rather at 1P, you would have gotten the same thing. That's because KP contains this transposition matrix that allows you to say that this is equal to that. Now, why is this useful? Well, the P1 and the 1JP, they look familiar because of that. So that list of P plus 1 elements that we have here is a well-known list of P plus 1 elements. It's related to the Hecke operators. We also choose a H measure on the periodic group, and we normalize it so that the compact group has measure 1. And voila, there's a third definition of the Hecke operator. And this third definition is you take this weird looking set and you consider its characteristic function. That's a nice continuous integrable function on the periodic group. And then whenever you have a continuous integrable function on your group and you have a group action of that group on the space, you have a convolution operator associated to it. It's just like convolution of on R or on the torus, except this time you have one function on the space and one function on the group, and then the convolution gives you a function on the space. Everyone is happy with that? That's the definition of a convolution operator, or does someone want to see a definition? Okay. And then one has to do a calculation. Namely, one has to check that this third definition is indeed yet again another definition of the same operator. And as time passes, I refer to the notes once more. There's something else that comes out of this rather quickly, if you believe the third definition, namely that TP is a self-adjoint operator. And that's a corollary of this equation here. Because when you take the inverse of that set, you take this comes over here, this comes over here, but they're the same anyway, so it doesn't matter. And then you get the inverse of P1, right? But what's the inverse of P1? Well, it's P to the minus 1, 1 but that's 1p. Because you can multiply freely by p times the identity. So what this strange looking equation says is that the set is equal to its inverse. And when you have measure preserving action, right? And you have a group element acting, then the adjoint of the group action is the action by the inverse. Because when you are measure preserving, you're not just preserving the measure, you're also preserving the inner product. That means you're unitary, and if you're unitary, then the adjoint is the inverse map. So when you convolve with a characteristic function, the adjoint of that is the convolution with the inverse of the set. But the set itself is symmetric, so we get that it's a self-adjoint operator. Okay, this is now another important step. We have this space PGL2R cross PGL2QP, and then we quotient out from this the lattice PGL2C bracket 1 over P. And this thing here, this periodic group, acts on this space, right? I mean, it's a subgroup of the group that I take a quotient of. So of course this group acts on this space, and after I take the quotient by the compact group, the periodic compact group, the action isn't really, I don't have the action any longer, because when I quotient by a subgroup on the right, the only thing that can still act on the right is something that normalizes the group that I have a quotient by. Now the periodic group is simple here, so it doesn't have any normal subgroup, so there's no action left when I take the quotient by Kp. But what is left are the orbits of the big group. That is definitely something that I still have in my picture. So in the unit tangent bundle of the modular surface in SL2Z quotient out from SL2R, the orbits of this group exist in some sense. They are still there. The orbits exist, not the group action. And the orbits these orbits are isomorphic to PGL2QP mod PGL2CP. And this is the reason why we want to look at that space, at that quotient space, PGL2QP mod PGL2CP. You should think of this as the periodic analog of the hyperbolic plane. Why? Because had we written here R, then this would be just PGL2 of R. And then what's the analog of PGL2CP? Well, PGL2CP is a maximal compact subgroup of PGL2QP. So the analog of this thing would be PGL2 of R mod SO2. which is the hyperbolic plane. So this is the periodic analog of the hyperbolic plane, and this is sort of the periodic analog of the unit tangent bundle of the hyperbolic plane. Some sense. Of course, that all is true, but there's also some crucial difference. This here is a combinatorial object, right? Because what we quotient out by is an open subgroup. So the quotient is a discrete set. So we are looking here at some combinatorial thing that should be the periodic analog of the hyperbolic plane. Of course, it needs to be a tree. So this is what the proposition over there says. For any prime p, the quotient PGL2QP mod PGL2CP is a p plus 1 regular tree. P plus 1 is not so surprising because of all the p plus 1s we have seen before. There's also the second portion where CP submodules are used. So that's, what is that? When you have CP is an open subgroup of QP, so CP squared is an open compact subgroup of QP squared, and you can just play the same game that we played yesterday, but this time with CP instead of C. What do I mean by that? The space of all deformations of CP squared up to homofatty equivalences is isomorphic to the quotient PGL2QP mod PGL2CP. Right, because PGL2CP is the stabilizer of CP squared when we let the element G in PGL2QP act on it. No surprise there, and I'm considering these subgroups up to homofatty equivalences, so that's why I have all these P's there. So in particular, I can now say if I have an element in this quotient, then I can think of it as an equivalence class of such submodules, CP submodules. And I'm considering two elements, and I want to know whether they are adjacent in my tree structure. Right? I'm claiming I have a tree, so I need to ask when are two equivalence classes adjacent? Well, they are adjacent if I can choose the representatives so that one is an index P subgroup of the other. Okay. So what I mean is not really the whole picture that I drew. What I mean are just the vertices. I don't mean the edges. And hence I need to define some extra thing, namely what it means for one to be adjacent to another. Sorry. So this would be P equals 2. And hence P plus 1 is free regular tree. That's always because you have to look at the projective line, and that's the P plus 1. So the object consists of countable many dots, but as such it's not so interesting because I don't want to think of it as the natural numbers. So I also think of the adjacency relationship that I define. But as an abstract object, it's just a countable set, together with a relationship that says whether two elements are adjacent or not. Yeah, I mean, it shouldn't be surprising because the hyperbolic plane is sort of really very close to a tree, and also lattices in SL2R are often sort of free objects, and this is it's also a free object without any. So one has to prove that, but again, I want to spend my time differently, so I will assume that and hope you have the time to look at the notes, because it is proven in the notes. And feel free to ask me if you get stuck reading this. Right, so what comes next? Next comes somehow study of the Hecke operators, not for the prime, but somehow for, we want to go further into the tree. The Hecke operator, I haven't said that, but it will be important. The Hecke operator is actually the following. You take a function defined on the tree, and then you replace that function by 1 over p plus 1 sum f of w adjacent to dot, right? I mean, what you get is a function, so the function needs to take an input, the input goes here, and then you look at all the adjacent vertices, and you look at the values of the function on the adjacent vertices, you average, right? So the picture is you average over the neighbors, and that's the p Hecke operator. And here we generalize that picture. We forget the averaging, meaning forget the incorrect normalization, and average over the distance k neighbors. Right, you have this combinatorial object, you know what the neighbor means. Neighbor is a one neighbor, and then you know what the distance 2 neighbor is. So this is the set of distance 2 neighbors from the middle that I drew. And again, this object of summing over the distance k neighbors, I defined it here, I defined it on the tree, so that means I defined it on PGL2QP mod PGL2CP, but that object lives inside the unitangent bundle of the hyperbolic plane. So I get some operator that acts on functions on the unitangent bundle of the hyperbolic plane. And after some calculation, you get that it's this operator. Just so that we recall that later that these summation operators over the neighbors, when I talk about the p plus 1 regular tree, that has something to do with the model surface and the real world. Okay, now another classical subject. We considered the Casimir operator and all these universal developing algebra business for the hyperbolic plane to build the microlocal lift. And this is a very classical story, a lot of history. And here we use the periodic analog in some sense. We also have to dig in and find some classical object that helps us to analyze what's going on the p plus 1 regular tree. And the Chebyshev polynomials of the second kind are precisely the tool that helps us to understand the behavior of Hecke eigenfunctions. So what's that? It's just some sequence of polynomials. That's it. That's the Chebyshev polynomials of the second kind. You define it recursively. That's it. Now, if it were only that, it wouldn't be so useful to us. But actually, there are closed formulas for these polynomials. And you prove these identities just with addition formula of sine and the additional formula of hyperbolic sine. So That's completely elementary to check. Again, it's in the notes. Okay, so why the heck do we look at these polynomials? And here's the reason. Forget now the hyperbolic plane. Just look at the p+1 regular tree. Then you can define this operator. UNF at the vertex V is equal to some normalization, sum of all the k's, less or equal than n, but k should have the same parity as n. And then you sum of all the neighbors at distance k from the vertex V, and you sum the value of the function at these distance k neighbors. So that looks horrible. What does it mean? Let's draw it again. For p equals 2. For p equals 2, we have this p+1 regular tree. That's the vertex in the middle. That's V. Right, and then it continues. If n is equal to 1, all we are doing is we're summing over the neighbors. So then it's the classical Hecke operator. This U1 is the TP, not from my lecture, but the TP from Sound's lecture. If n is equal to 2, then we are summing over the distance 2 neighbors. And the vertex. That's just the right thing to do. But we don't sum over the distance 1 neighbors when n is equal to 2. And then it keeps going like this. Sometimes we sum over the neighbors and other stuff, and sometimes we sum over the vertex and the distance 2 neighbors and other stuff. Okay? The claim is that these operators have relations. And well, the first one is the identity. Yeah, should be clear. The second one is just our Hecke operators, no matter how we want to normalize them. And then the n plus first is equal to this guy, where again the SP is just summing over the neighbors and the TP is the averaging. And that's the relationship that is claimed. And the proof of this is not difficult, because you should just try to envision what happens when you compose this operator for n, which is here, when you compose this operator for n with the summing operator over the neighbors. Right, so you are here, you want to calculate the UN of f composed with the SP. So you need to evaluate what the UN of f does at the distance 1 neighbors. Right, so at this point, and this point, we have to calculate UN of f. UN of f does what? It looks at the as far out as distance n. So it goes as far as distance n. Into this tree, but also back into this tree, right? And if it goes back, here it only goes to distance n minus 2, because it first needs to go back to V, and then it needs to go to the other branch, and then viewed from this vertex, it's now going out further up to distance n minus 2. So maybe I should have said this is distance n plus 1 from the vertex, from the origin vertex. It's distance n from here, but then it's distance n plus 1 from the origin vertex. So here it's distance n minus 1 from the origin vertex and also distance n minus 1. But then from this vertex we go to distance n plus 1 into this guy, so it becomes symmetric, and also to distance n minus 1 into this shell and n minus 1 into this shell, which is also happening from this side. And then from here we go as n plus 1, and again here and here. So it becomes the overlay of 3 different things. So we definitely should be seeing something that goes out distance n plus 1. We definitely see an n plus 1 there. But at distance n minus 1, there is sort of more happening, right? There will be some multiplicity in the count. And this formula, when you analyze it, takes precisely care of all the multiplicities that are produced by this procedure. Everyone is asleep. Okay. This is the main proposition. What does it say? You take an eigenfunction on the p plus 1 regular tree. So this is a completely abstract proposition. You just take a p plus 1 regular tree, you take an eigenfunction of it. For what operator? Well, for the summing operator over the neighbors, or for the averaging operator over the neighbors. And that eigenfunction actually also becomes an eigenfunction for this operator just because of these recurrence relations. Because these recurrence relations show that these guys are polynomials in the summing operator. And actually these relations here are of course precisely these relations. I didn't say that, but here. They're the same thing. You just need to figure out what the x should be, but it works out. We assume that we have real eigenvalue. For this abstract proposition, we assume that we have real eigenvalue. That's okay because we know that the Hecke eigenvalue, when we think of a function on the modular surface, has a real eigenvalue. Why do we know that? Because we checked that the Hecke operator is self-adjoint because of the symmetry of the set that we saw before. So we can assume we have a real eigenvalue. Then there's this claim that when you go into the tree and you sum the eigenfunction over the neighbors at distance n or less, absolute value squared, so that's an L2 estimate over a large sphere, that sum is greater or equal some constant times n is how far you go, times the value of f at the origin squared. That's the claim. Let's just see what this tells us. For instance, it tells us that the averaging operator on L2 of the p plus 1 regular tree can't have eigenfunctions, right? Because if you have an L2 eigenfunction, this should hold for all n, and there's an n here, so the L2 norm is infinity, right? So there are no eigenfunctions for the p plus 1 regular tree, which is related to this statement. This statement is now a statement for the microlocal lift. And let's just see what it says. We take a non-negative function and we apply the summing operator over the distance k neighbors from k equals 0 to n to this function f, which we defined before. And we integrate the outcome over the microlocal lift measure. Then this integral is greater or equal than c naught times n times the integral of f with respect to mu. So let's believe this formula, and let's consider this problem. This is what we want to prove. This is what we know. This is abstract in some sense. This is for an eigenfunction on a tree. We don't know what it, maybe you do now, but let's pretend we don't know what this has to do with that, because this is some statement for the microlocal lift, this is some statement for the tree, but let's see how it relates to one another. What we are interested in, how is this defined? How are these expressions defined, right? For instance, this expression, that's the simpler one. How is this defined? Integral f d mu. That's the limit of f phi twiggle absolute value squared dmx. Right? This expression converges to this expression. That's the definition of the microlocal lift. I think there was a twiggle there. In this chapter disappeared. Now I can rewrite what that is. That's the natural inner product of f with phi absolute value squared. Let's rewrite this expression in the same way. If I rewrite that expression in the same way, I get the inner product of the sum of the SPK applied to f, absolute value phi twiggle squared. Right, the idea is that this expression for the eigenfunctions phi that I'm considering converges to the left-hand side, and this expression converges to the right-hand side, except for the n0n, which we want to see happening. Now, what do we know about S? We know it's self-adjoint. So this whole thing we can move over to the phi. That's equal to f sum SPK of phi twiggle squared inner product sum over the case with the same condition as we saw it in the other slide. Just because of self-adjointness, I can move this over. But now I just consider this expression, and I know that there's this relationship between the S operator on the modulus unit tangent bundle of the modular surface and the S operator when I think of just the trees, which is what this is talking about. And the phi twiggle, yes, is L2 on the modular surface or the unit tangent bundle of the modular surface, but I just restrict that to the tree. And then nobody tells me that it's L2. However, someone tells me, all the assumptions that I made, they tell me that when I restrict my phi twiggle to the tree, I get precisely such an eigenfunction. So this sum here is at every point greater or equal C naught n absolute value phi twiggle squared because of the lemma, because of this theorem. And my assumption was that the f, my assumption was here that the f is non-negative. So when I have an inequality for this thing and my f is non-negative, I get precisely this inequality that I wanted. So this is the thing. This is the important thing, so that we can get this corollary which tells you something about the microlocal lift. And yeah, this will tell you the recurrence that we haven't defined. Let me finish by saying a little bit about the proof of that inequality. That really uses all this Chebyshev stuff that I mentioned before. And the proof splits into two cases, and the split into two cases relates to what sound is telling us, whether or not we have the conjecture estimate on the eigenvalues. So there are two cases depending on whether the eigenvalue satisfies the conjecture or whether the eigenvalue doesn't satisfy the conjecture. And it's actually quite nice because we have two recurrence relations for the Chebyshev polynomials. There are two recurrence relations, and it depends on the value of x which one you want to reuse, right? If this x here is between 0 and between -1 and 1, then you would like to use the first one. That's the tempered case. That's the case which is conjectured. But if the x doesn't satisfy the conjecture, then it's this recurrence relation that you want to use. But actually, this function is very easy because it's monotone in n, and very concretely so. I mean, you can easily estimate this guy as saying this is, no matter what the theta is, right? The theta we don't know because the eigenvalue we don't know. That's the difficulty in that theorem, that yes, there's an eigenvalue, but we were not given any information about it. So we don't know in which case we are, and even if we know in which case we are, we don't know what the theta is. However, that expression is always greater or equal to n plus 1. And that's a very helpful and easy estimate because it's independent of the theta and it makes life very easy to obtain this. I mean, you need Cauchy-Schwarz and you need this, that this is greater or equal to n plus 1, and then you get, in the non-tempered case, this estimate. In the second estimate, in the conjectured case, in the tempered case, you have to work with this expression. But that's more tricky because this n plus 1 theta oscillates, and it may or may not be big, which is what we want, right? We want that expression to be big, which relates to the un. And then one has to argue a bit more by cases.